Hey there and welcome. Ever just stared at something floating and wondered why? Why do some things float and others sink? It seems so simple, right? But there's this amazing secret behind it all. A fundamental law of physics that explains everything from a tiny piece of wood to a gigantic steel ship. So let's dive in and crack that secret wide open. Okay, for the next few minutes, we're going to be physics detectives. Our mission, should we choose to accept it, is to solve a mystery you've definitely seen 1,000 times, but maybe never really thought about. The great float or sink mystery.
And here it is. This is our central puzzle. It is a genuine head-scratcher. You've got this enormous ship, right? Thousands upon thousands of tons of steel just cruising on the water. But then you take a tiny little nail made of the exact same stuff and plop, straight to the bottom. How on earth is that possible?
And this right here, this is the paradox in a nutshell. You can see the problem clear as day. On one side, something huge and heavy that floats. On the other, something tiny and light that sinks. It's the whole reason we're here. And to solve it, we need to find our first major clue. That first big piece of the puzzle, and honestly, it's the most important one, is a little concept called density. I'm telling you, if we can really get our heads around this one idea, we are more than halfway to cracking this entire case. So what even is density? You see the formula D equals m over v. But what does that really mean in plain English? Well, think of it like this. Mass is just how much stuff an object is made of. Volume is how much space that stuff takes up. So density is simply how tightly all that stuff is packed into that space. That's it. Okay, this really helps make the whole idea click. Imagine you have a kilogram of fluffy cotton and a kilogram of heavy lead. They have the same mass, right? But the cotton takes up a huge amount of space. It's not packed tight at all, so it has a low density. The lead, on the other hand, is super compact, giving it a really high density. Or flip it around. Think of a block of iron and a block of wood that are the exact same size. The iron is way, way heavier because its stuff is just packed in so much tighter. It is way denser than the wood. And here are the actual numbers that prove it. Now let's just focus on our three key players for this investigation. You've got water, which has a density of exactly 1.0. Then there's wood at about 0.7, so that's less than water. And iron, whoa, it's way up at 7.8, much, much denser than water. You're going to want to remember those three numbers. They are the key to everything. Okay, so knowing what density is, that's one thing. But as good detectives, we need to know how to actually measure it. We need the right forensic tools for the job. Now, for a simple shape, like a perfect little cube, it's pretty straightforward. First, you find its mass. Just pop it on a scale. Second, you calculate its volume. Easy enough, just length times width times height. And finally, you just plug those two numbers into our handy density formula. Done. But wait a minute. What if our object isn't a nice, neat little cube? How in the world do you measure the volume of a lumpy, bumpy stone? You can't just use a ruler for that, can you? Nope. This is where we need a much more clever technique. And here it is, the displacement method. This is pure genius. You just put some water in a measuring cylinder and write down the level. Then you gently lower your weirdly shaped object in, and what happens? The water level rises. Well, guess what? The amount the water rises is exactly equal to the volume of the object you put in. Once you know that, you can calculate its density just like we did before. This method is so classic, there's even a special tool designed for it. It's called a Eureka can. It's built to overflow perfectly, letting you catch and measure the exact amount of displaced water. Pretty cool, huh? All right, detectives, we have our main clue, density. We have our tools to measure it. Now it's time to bring it all together with the single powerful principle that governs everything, the law of flotation. So what's really happening when you put an object in water? Well, it's basically a battle between two powerful forces. You've got the object's own weight, thanks to gravity, pulling it down. But at the exact same time, the water is pushing back up with a force we call the buoyant force. And believe me, the winner of this epic tug-of-war determines everything. So the outcome of this battle really comes down to three simple rules, all based on density. Rule number one, if your object is denser than the liquid it's in, like our iron nail in water, its weight easily wins the battle and down it goes. It sinks. Okay, rule number two, what if the object's density is exactly the same as the liquid's? Well, then it's a perfect tie. The downward pull of its weight is perfectly balanced by the upward push of the water, so the object doesn't sink and it doesn't float to the top. It just hovers, suspended right there in the middle. And finally, rule number 3, the one we've all been waiting for. If an object is less dense than the liquid, like that piece of wood in water, the buoyant force from the water is actually stronger than the object's weight. The upward push wins and it floats. So, we have the law, we have the rules. Now it's time to apply all this knowledge and finally solve our cases. We're talking everything from those giant steel ships to the secrets of submarines. Let's see how it all works in the real world. And here it is, the moment of truth, the solution to our big mystery. A solid steel nail is, well, it's solid steel. Its density is 7.8, way higher than water's 1.0, so of course it sinks. But a ship isn't a solid block of steel. It's a cleverly shaped hull that's filled with a massive amount of air. So when you combine the super dense steel with the super not dense air, the ship's average density as a whole drops to less than 1. And that, my friends, is why it floats. And you know who takes this principle to the absolute next level? Submarines. They are masters of changing their own density on command. To dive, they open up special tanks and let water flood in, which makes their average density greater than water, so they sink. To come back up, they use powerful compressed air to blow all that water out, making themselves less dense again so they rise to the surface. It is just brilliant engineering. And what about icebergs? Well, ice is a pretty weird substance. It's one of the few things where the solid form is actually less dense than the liquid form, and that's why it floats. But here's the catch. Its density is about 0.9, which is really, really close to water's 1.0. This means that to float, it has to push aside a huge amount of water, leaving about 9/10 of its gigantic, dangerous mass hidden just beneath the surface. And it all comes down to this one beautiful, elegant, scientific statement. The weight of a floating body is equal to the weight of the liquid it displaces. It doesn't matter if it's a tiny cork or a massive aircraft carrier. This law is always true. That right there is the secret of flotation. So there you have it. The great floater sink mystery is officially solved, and it's all thanks to the power of density. It's such a simple idea, but it allows us to build these incredible things that conquer the oceans. So I guess the only question left is, now that you know the secret, what would you build with it?